Okay, welcome to the last lecture for section 4.4 on curve sketching and concavity. And we're going to carry on with what I call non-standard graphs. And so we had a few in class already, and so the next sort of type of graph you all saw on your last quiz, and it involved the function e. So here's an example. Other examples could be x, e to the x, x squared, e to the minus x, any sort of combination like this. Okay, and once you get a handle on these, they're not too bad. So we're just going to go through all of our steps. The first derivative here is e to the minus x e to the minus x. Set this is equal to 0. If and only if e to the minus x times 1 minus x equals 0. And this gives us a critical point at x equals 1. And remember, e to the any power minus x is greater than 0 for all x. Okay, so we make our sign chart for f prime of x. We put in our critical point. We put in e to the minus x here. That's positive everywhere. We put 1 minus x in. It's negative here and positive there. So the function's increasing there and decreasing here. So local min at 1 comma 1 over e. The function's increasing from minus infinity to 1 and decreasing from 1 to infinity. So we got a local minimum, local max. Excuse me. All right, let's take the second derivative here. And that's going to be minus e to the minus x minus e to the minus x e to the minus x. And that's equal to x e to the minus x minus 2e to the minus x. We set that equal to 0. And that's true if and only if e to the minus x times x minus 2 equals 0. And so that gives us another critical point at 2. Okay, so now we do a second derivative test. I got 2 there. We plug in e to the minus x, that's positive everywhere. We plug in x minus 2, it's positive there and negative there. So concave down and concave up. So x equals 2 is an inflection point. And that's at what, 2 comma 2 over e squared. And it's concave down on minus infinity to 2. Concave up on 2 to infinity. All right, so now we're ready to graph. Are there any zeros? What does this equal 0? At x equals 0, and that's also the y-intercept. So we only have one non-calculus based data point, and that's that. Let me change colors here. There's a 0 or a y-intercept there. We have critical points at 1 and 2, 1 over e, 2 over e squared, I think. Okay. So our max is here at 1 e. We have an inflection point here. And so this thing is what? Concave down along there, and then it's concave up along here. And we have a horizontal asymptote at y equals 0 in the positive direction here. So that's the graph. And so we add that to our list of non-standards. So what have we seen so far? We've seen types of curves. We've seen polynomials, like f equals x cubed plus x minus 1. We've seen rational functions, like r of x is x minus 2 over x plus 1. We've seen non-standard, I'll call it form 1, stuff like f is equal to x to the 2/3 times 5 minus x. And then we have non-standard 2, which is stuff with ln. So something like g of x is x times the ln of x. And remember, the domain for ln is always 0 to infinity. No negative numbers and no 0. And this last one we've introduced, non-standard, involve e's. So e to the x, xe to the x, xe to the minus x, x squared e to the minus x, etc. And I think that's pretty much all of them. I do remember seeing one on homework with something like this, square roots. And that's almost rational. It's got a square root. Remember your domain on square roots. Whatever's inside has to be greater than or equal to 0. And that's really it for curve sketching. The last part of the section that I really enjoy is how to find a curve of f of x, give an f prime of x and or f double prime of x, and maybe a point. So let's see here. Here's my example. Let f prime of x be the blue curve and f double prime of x be the green curve. Find f of x through the point P that satisfies f prime and f double prime. Okay, so here I'm going to make my axes white. I'm going to put in minus 2 and 2, and I'm going to put in the point here P on the y-axis. Okay, so the blue function, is that right? Yeah, the blue function is f prime of x. And it goes through minus 2 and 2. The green function is f double prime of x. Cool, so what's a possible graph for f? So what you do, and this is a really cool way to do these problems, is you make a sign chart from the graph. So where is f prime of x equal to 0? F prime of x is equal to 0 at -2 and +2. That should be a plus, right? So I have critical points at -2 and +2. Right, so here, so I'm just going to put f prime because we don't know what it is. To the left of -2, f prime is positive. In between -2 and 2, f prime is negative, and to the right, it's positive. So we have plus, minus, plus, so it looks like this is the graph of f. F is going to be increasing from minus infinity to -2, decreasing from -2 to 2, and increasing from 2 to infinity. So let's try and draw this graph here. I'm going to make it purple. Actually, let me make my axes white here. There's that point P that's got to be on there, right? Okay, so we're going to make this purple. So go away. So there's a local max at -2. So I'm going to put that up there. And there's a local min at 2. I keep doing this silliness. It's not negative, it's positive. So let's see, the function is increasing to -2. It's decreasing to 2, and then increasing afterwards. And it goes through P. It also looks like P is an inflection point. At 0, P. And let's look back at this guy here in green. If I make a sign chart for f double prime of x, sure enough, it's got a critical point here. It's where it's 0. So it's negative here and positive here. It's down, concave down and concave up. And sure enough, this is concave down, and this is concave up. So that works. And it's not the only answer. There's lots that work. But this one is good. All right, that's everything from chapter 4.4. For guided practice. To problem 4.438 and 4.482.